Hello there. I'm Dr. Joseph, and today we've got surface area of surfaces of revolution. All right, so this is the formula. It's a little bit scary. Hopefully, this part of the integrand looks familiar. This should remind you of the arc length integrand because that's what it is. Um, so we're not going to go through a full derivation this time, but I'm going to quickly show you the idea of where that comes from. Okay, so this is the OpenStax textbook. Here's a nice picture of a surface of revolution. And you should always think integrals are limits of approximations. So in order to come up with an integral, we first need to come up with an approximation of the surface area. And the way that turns out to be most sensible to do this is to first approximate the arc length. So approximate the curve itself with straight line segments, just like we did for arc length, and then revolve each one of those segments 360 degrees, producing this sort of roundish top looking figure. Um, and what are those shapes that you get? You may not know this word, but they're called frustums, which is basically just part of a cone where you chop off the top. And to approximate the surface area, we need to know the surface area of a frustum, which is 2 pi times the average of the radii, the top and the bottom radius, times the slant length, L. So anyway, you would add that up for each one of your subintervals here and take a limit. And the formula that ends up coming out, so that the reason that square root 1 plus dy dx squared comes up is because that is the slant length of each of those little frustums. So that's in there, and also 2 pi times f of x, because remember f of x is like the radius. So if you're interested in dissecting that more, you can read the book or ask your instructor about it. But I just wanted to say a couple words to motivate it. So get the slides back up. One thing to note about this formula is we just have f of x there. So this is um, technically assuming the values of our function are positive, right? So your f of x is above the x-axis. If it were to dip below, we would need to take the absolute value of f of x in order to count all of that surface area as positive. Um, just something to be mindful of. And let's do an example. So as with arc length, you're going to find that a lot of these problems are hard to integrate by hand. But this is one that we can. And it says we're going to rotate y equals x cubed over the interval 0, 2. So hopefully we sort of know what that looks like. And on the interval 0 to 2, that is positive, right? So we don't have to worry about taking the absolute value of anything. So that means our integral is just going to be 0 to 2, 2 pi, and then f of x is x cubed. And then I need the square root of 1 plus, so dy dx is 3x squared. And then I need to square that. So I get 9x to the fourth dx. Okay, so that's the integral for the surface area that we get when we take this thing and revolve it. So it's going to kind of be cone-like. And how would we actually do this integral? Well, luckily, we can do a u substitution. So make u be 1 plus 9x to the fourth, and then du is 36x to the third dx. dx is du over 36x cubed. And 2 pi. I'm going to write this as square root u times x cubed times du over 36x cubed, so that I see my x cubes cancel and I have only u's. So the u substitution was successful. I'm going to change the bounds. So when x is 0, u is 1 plus 0. And when x is 2, u is 1 plus 9 times 2 to the fourth, which is 16. And 9 times 16 is 3 times 3 times 4 times 4, which is 12 times 12. So that's 144 plus 1 is 145. So we have changed our bounds, and now we're totally in terms of u. I'm also going to cancel 2 and 36. All right, so together we have pi over 18 integral from 1 to 145 of u to the 1/2 du. So that's going to be pi over 18 u to the 3/2 divided by 3/2 evaluated from those bounds. And dividing by 3/2 is multiplying by 2/3. So in the end, 2 pi over 3 times 18. And you can cancel a little bit more. So this is going to be pi over 27 times 145 to the 3/2 minus 1 to the 3/2, which is 1. And that is approximately 203 square units. So whatever your unit of length is, you need to square it because this is an area. All right, so that's example 1 that we were able to do completely by hand. So we just have one more example to try yourself, and this one says set up but do not solve the integral to find the surface area, where we have f of x is square root x squared plus 5 rotated around the x-axis on the interval from -1 to 2. So give that a shot and pause the video. 3, 2, 1. Here's the answer. And again, don't try to work that out. It's not an easy integral, but I like to give little reminders. If you were to go one more step in simplifying this, what you would get there is x squared over x squared plus 5. Okay, inside that square root. So that is all for this video, and have a nice day.